In recent decades, there has been a growing case for the theory of quantized gravity, the idea that space and time are digitized. But how could this be possible? And what does it really mean? And even more curiously, what would be the nature of reality beyond the quanta? Thus far, we have identified the biological surface where the flimsy, influenceable and ever-changing self gets presented to us, where the brain lies the mind into existence. But much of our discussion has been concerned with this issue of change, of a self experienced in time. So let us return to our earlier topic of time and see if a deeper knowledge of its hows can't offer some insight into this ever-shifting theory of self.
Good morrow, fellow humans. My name is Sean and I am obsessed with infinity. So join me as I attempt to unpick the infinities of what is.
In 1950, physicist John Wheeler proposed that at the scale of Planck's constants, Planck length and Planck time, we hit upon the smallest possible lengths in the resolution of spacetime, below which Wheeler theorized a flux of quantum foam, a place where concepts such as left, right, up, down, near, far, and even now and then become so scrambled as to have no meaning. An idea that is so counterintuitive that we hardly have a language capable of describing it. Practically every word is in some way bound to either a spatial or temporal framework. And yet, in this strange and alien landscape, even the claim of being below this scale becomes nonsensical. But what is it about Planck's constant and its underlying equation that suggests a description of reality as radical as that offered by Wheeler? In the late 1800s, physics had hit a roadblock. A conflict between mathematical and experimental evidence that unveiled a definite flaw in the way we thought about atoms and the way they radiate energy. The understanding at the time was that black bodies, which is any body that emits electromagnetic radiation, be it a light bulb, a star, or even a human, should be capable of emitting this radiation via any frequency found along a continuous spectrum. And as these frequencies become further compressed and move towards higher and higher energy states, one should also find a corresponding linear increase in the emitted radiation. Essentially, what this would mean is that the more we push into higher frequencies of light, transitioning from reds to blues, the closer that radiation levels should reach towards infinite energy. But considering that blue light fails to showcase the qualities of a death ray, we know for a fact that this is not what happens. Instead, at a particular threshold, the radiation level unexpectedly bottoms out. Dramatically dubbed the ultraviolet catastrophe, it was Max Planck who, in what some have referred to as a frustrated last-ditch effort, altered the equations, theorizing that it was impossible for atoms to emit radiation at fractional dissections of particular intensities. And almost accidentally, it solved all the problems. All observational data matched Planck's calculations, and thus the quantum theory of energy was born. Energy, it turned out, was quantized. This theory, confirmed in a related experiment by Albert Einstein only a few short years later, showed us that even light was made up of these minuscule packets of energy. Photon-sized bundles of energy that pass from one electron to the next. A world of parts, giving rise to not only light, colour and heat, but also the repelling force we feel when pushing up against a solid object. Everything, every force, was made of fundamental quanta. Everything, that is, except for gravity. It wasn't until the theory of relativity came along in 1905 that the true implications of Planck's discovery could be made clear. By combining the three now known fundamentals of Newton's gravitational constant, Planck's own quantizing constant, and Einstein's limitations on the speed of light in a vacuum, Max Planck could now describe a measurable quantum limit. The Planck length was 1.616255518 by 10 to the power of minus 35 metres, a fundamental unit that could describe the minimum length, duration or mass of energy. And the smooth, non-quantized description of gravity found its place as the warping of space-time. Gravity was space-time, the backdrop to the quanta. There was only one problem. It still didn't work. Actually, it worked extremely well, except for the fact that our understanding of gravity with respect to the very large and gravity with respect to the very small didn't form a unified theory. Instead, we now had two very distinct ways of describing our universe, relativistically and quantum mechanically. Each accurate and, according to all observational data, correct. It's just that they didn't work together. A unification of classical and quantum physics is still today considered the holy grail of physics. But it has been this hint that gravity is the only force in our universe not to be quantized that has since led many to assume that any theory of everything should likely include a quantizing of space-time as well. The universe, they say, could be conjured by pure mathematics. And it is this that led Dr. John Wheeler to hypothesize his idea of quantum foam, the domain beyond, where space-time fails to operate as a continuous analog agent. Planck's constant, denoted by the letter H, can be found at the heart of any quantum mechanical theory, especially those attempting to bridge the gap between relativity and quantum mechanics. Theories such as quantum loop gravity or string theory go so far as to include Planck's constant alongside Wheeler's theory of quantized gravity, suggesting that time, at a fundamental level, might not exist as a continuous agent, but instead emerge as a property of the fluctuating quantum units of space. In superstring theory, this quantizing of space-time can, in extremely basic terms, be visualized simply by imagining a shrinking circle. If the nature of this circle were quantized, then there would have to be a minimum value that it could shrink before turning in on itself and beginning to grow. These theories also talk to the mysteries at the start of the universe and suggest that rather than the universe beginning with a bang, it may have begun with a bounce. As one universe ended, passing through the eye of the space-time needle, it turned in on itself before expanding outwardly in all its current directions. Such a granular nature of space-time would also eliminate universal infinities and singularities, previously argued as an inevitable occurrence of nature. Quantum loop gravity, similarly, describes reality at the Planck scale as a net of finite loops. To represent space-time in their calculations, physicists use a 3D grid called a lattice of quantum chromodynamics, or LQCD. Upon this, they calculate the actions of the quarks that make up the protons and neutrons of an atom. Upon the lattice, force-carrying gluons move about in a beautifully complex dance, with each element influencing the next, building towards a chaotic complexity that can only be untangled with our most powerful of supercomputers. When first attempting to rectify the enormity of this mathematical puzzle, Schrödinger, in his correspondence to Einstein, referred to it as a gift from the devil's grandmother. Using the LQCD, physicists place the quarks in their respective positions alongside the force-carrying gluons that hold the quarks together. Then, step by step, they close the gaps between the quarks, taking into consideration all the many complex variables. At Planck scales, due to a charge of energy inherent in the gluons, they found that gluons would spin upon themselves in a loop outside of their relationship with the quarks. These were loops of force, loops of gravity. And it's these loops that inspire the theory. For these loops don't exist somewhere within space-time. They are space-time. Loops that knot and weave together to form a net called the spin network, thought to be the smallest resolution of space-time, the quanta of volume, area, and duration. However, there is no evidence in either model to support a claim that such a quantizing of space, if found to be true, should be a final or ultimate roadblock in the path of reality. And neither is this what the theory's proponents are attempting to prove. If real, this would merely be the scale where the geometry associated with directions in both space and time become emergent in their known forms, hence the chaotic flux of Wheeler's foam. Like all previous examples of emergence, we are never offered any ultimate one-sided boundary. Just as at the scale of the atom, we pass beyond the scale of matter, and at the scale of the photon, we pass beyond the scale of light. Here, we may pass beyond the scale of space and time itself, into the next perspective of this infinite flux. Time would, therefore, have an emergent nature, not too dissimilar from how a wave upon the ocean emerges from the molecular connectivity of water molecules, or how our fluid consciousness emerges from the quantized firing of neurons. But what I feel that these and all other examples of emergence share is a quality of perspective, highlighted by the fact that emergent properties are not secondary to their more elementary parts, at least not in any ultimate sense. And this idea of emergence is one that we're going to have to spend some time on, which is what we're going to do next week in the second half of this chapter, the digital and the spaces between. Good morrow, fellow humans. Thank you so much for spending your time with me, for joining us once again. If you would like to jump ahead to the very next chapter, well, you can do so by clicking this link that will be here as soon as the chapter goes live, or if you want to take yourself back to the start of the story and catch up to discover where we're at, you can do so by clicking this link. Otherwise, much love, and I hope you all have a wonderful, wonderful week. See you later. Bye.